Alright guys, so you all are group number 3 and you've been assigned the third type of reaction that we cover, which is combustion. This is the one that we may be most familiar with just in everyday life. This is what allows our cars to run. This is what's going on in your engine. It kind of gets you from place to place. I know this is a big year with a lot of you all getting to drive, so that's how it affects your everyday life. But what it is, kind of on the chemistry level, is you take a hydrocarbon, and that's just simply a compound that has both carbon and hydrogen, and you react it with oxygen, which typically, we have in air, and the products that you get out are carbon dioxide and water, okay? And so the nice thing about combustion is it's a very consistent reaction. The same products, carbon dioxide and water, are produced, every time. And it's always a hydrocarbon plus oxygen, okay? And so typically, we associate with combustion kind of with, fire or explosions. And so also, as a result, we typically have energy, released in the form of heat, and often light as well, okay? So again, here's kind of our basic structure of combustion reaction. And so what we're going to do is we're going to walk through 3 examples. And so you want to be able to use these kind of when you're teaching your classmates to help show them how you can write the products and then balance your overall reaction for combustion. So we're going to start with example 1, and that's where we have C2H4. So that's our hydrocarbon. And again, what's typical of a combustion reaction is that the other reactant will be oxygen, and it'll be O2 since oxygen is a diatomic element. And then one thing that you'll be asked to do is to predict the products of the reaction. But for combustion, what makes it really nice is that the products will always be the same. They'll always be carbon dioxide and then water. So those you can just fill in immediately, okay? So then the last thing that we want to do is go back and balance our equation to make sure that the number of carbons on the left equals the number of carbons on the right, the number of hydrogens on the left equals the number of hydrogens on the right, so on and so forth, okay? And so I'm going to give you some tips for balancing to kind of help make it easier. So first, I'm going to recommend that you start by balancing carbon. Second, by balancing hydrogen. And then third, by balancing oxygen. If you do it this way, it just makes the balancing kind of work out a lot more easily. All right, so let's start with our carbon. So if we look on the left, we see where we've got 2 carbons, but on the right, we only have 1. So again, to balance, I'm going to be changing my coefficient. So I'll put a 2 in front of my carbon here, okay? So now my carbons are good. I've got 2 on the left and 2 on the right. So now I'm going to move on to my hydrogens. So if I take a look right now, I've got 4 hydrogens on the left, but I only have 2 on the right. So if I want to get up to 4 hydrogens, I can make my coefficient 2, since 2 times 2 will be 4 overall. So now my hydrogen should also be balanced. All right, and last but not least, we're going to get down and balance our oxygens. So if we look on the left, in this case, we've got 2 oxygens, but then on the right, we have to account for the oxygens that are both in carbon dioxide and water. So if we look at carbon dioxide, the entire molecule has a coefficient of 2. So if I take 2 times 2, that means that in carbon dioxide, I've got 4 oxygens. And then if I look at water, it's got a coefficient of 2. 2 times 1, I've got 2 oxygens here. Okay, so if I combine those together, that means that total, I've got 6 oxygens on my right side. So if there are 6 oxygens on the right, that means that I also need 6 on the left. So if I go back and look at my O2, it's got a subscript of 2, so I'm trying to think, okay, what times 2 would get me to 6? Okay, and so that's our handy dandy 3. So if I take 3 and multiply it by 2, that gets me to 6. So now I've got 6 oxygens on both sides, and so it's balanced as well. Okay, And so that would be kind of my final answer to the problem. All right, so now let's try our second example. Okay, we're actually going to do ethanol. You may have seen this at the pumps where it says your fuel, contains such and such percent ethanol. So again, we're going to take our hydrocarbon, and that'll always be provided for you. And so we know that in combustion, it'll react with oxygen. And when we're predicting the products, it's consistent. You should always produce carbon dioxide and water. Okay. So now, just like before, we're going to go through our steps to balance our equation. So start with carbon. So on the left, I've got 2 carbons. On the right, I've got 1. So I should have 2. Okay, so now those are good. Then I want to do my hydrogens. Now, if you notice, on the left, I have a total of 6 hydrogens. I've got 5 here and then 1 here. So that's an understood one. So I've got 6 total. And so that means I need 6 on the right. So right now I've only got 2. So if I change my coefficient to 3, 3 times 2 will get me to 6. So now my hydrogens are balanced as well. Okay. So now, last but not least, I want to balance my oxygens. Okay. So if I look on my left, what I'm noticing is that I have 1 oxygen in ethanol, and I have 2 oxygens, just from oxygen by itself. So that's a total of 3. But if I look on the right side, I've got 4 oxygens coming from carbon dioxide and 3 coming from oxygen. So together, this makes 7. So I'm kind of short on my left side. Here's what I want you to think about. If I changed the number of oxygens by changing the coefficient of ethanol, I kind of mess up the carbon and hydrogen that I already have balanced. So what you want to do is when you're balancing oxygen, you're going to be changing the coefficient in front of oxygen just by itself. Okay? So let's think about this. So we eventually need to total up to 7, and we've got 1 oxygen and ethanol that's kind of fixed. Okay? So I know that to get to 7, I'm going to need 6 more. So now if I look at my just O2, if I make the coefficient 3, 3 times 2 gets me to 6, and then 6 plus 1 is 7. So now everything is balanced. All right, so moving on. Last example. Okay, so last example for you is C4H10. There's our hydrocarbon. And again, what's typical of combustion is that we combine it with oxygen and we produce carbon dioxide and water. Okay, so now let's get to the balancing. So we'll start with our carbon. If you notice, we kind of balance carbon and hydrogen based on what's on the left, and then we tend to balance oxygen based on what we start with on the right. So just in case, you hadn't caught on to that pattern yet. So we've got 4 carbons on the left, so I need 4 on the right. Okay. I've got 10 hydrogens on the left, so I need 10 on the right. I've got 2. So 2 times 5 will get me to 10. All right. So finally, we're ready to balance our oxygens. So we're kind of starting from the right. So if I look right now, I've got 8 oxygens coming from carbon dioxide. That's 4 times 2. And I've got 5 oxygens coming from my water. So if I add those together, 8 plus 5 is 13. Now, it kind of looks like we've run into a problem because I only have O2 over here. So 13 is an odd number, so 2 can't be multiplied by anything to go into 13 evenly. Okay, if I did 2 times 6, that's 12, and then if I did 2 times 7, that'd be 14. But I don't really have anything that would get me to 13 just straight away. So anytime you run into this issue when you're balancing, where you end up with an odd number of oxygens on the right and you only have O2 on the left, what I'm going to recommend you do is use something called the fraction method. So here's what I want you to think about. if I take 13 and put it over 2, okay, here's what happens when I kind of plug this in as the coefficient here. So what you're going to do is take however many oxygens you need, and you're going to write it as a fraction over 2, okay? And so what happens is, because this is O2, to find the number of oxygens that I have, it's always the coefficient times the subscript. So when I take 13 divided by 2, which is really like 7.5, and multiply it by 2, notice the 2's cancel out, and so I technically have 13 oxygens. Okay? So let me charge my battery right quick. Be right back. Alright, sorry about that. Okay. And so we were talking about the fraction method. And so if you take the number of needed oxygens and write it over 2, okay, then technically, when we place that kind of in our equation, 13 over 2 times the 2 that's in our subscript technically gives us 13 oxygens, okay? But here's kind of the problem. I can't end up with a fraction as my coefficient because I can't have 7.5 oxygen molecules, okay? So the last step that we're going to do is, once we've written our fraction coefficient, is we need to somehow get rid of that 2 that's in the denominator. So what we'll do at this point is we'll take our equation and we're going to multiply the entire thing by 2 so that this 2 in the denominator of our fraction will cancel out. Okay? So now what I'll be left with is I'll have 2 C4H10. And then remember, this 2 times 13.5 should cancel out and just leave us with 13 oxygens. Okay? And so then on my right, I've got to take my 2 and multiply it by 4. So that'll result in me having 8 carbon dioxides. Okay? And then finally, 2 times 5 will give me 10 waters. And so this would be my final balanced equation. We can go back and check ourselves. I've got 8 carbons and 8 carbons. I've got 20 hydrogens, 2 times 10. I've got 20 hydrogens here. All right. And then if I check my oxygens, 13 times 2 is 26. And then 8 times 2 is 16, plus 10 times 1 is 10. So that also totals up to 26. So everything is good to go. All right, but that's kind of as bad as the balancing gets. It's just remembering to use that fraction to kind of help you get to the correct coefficients to balance your overall equation. All right, thanks for watching.